let's move on to the second presentation with this marvelous duet, Playmodes.
Are this wonder duet called Playmodes. Here, that's how we call them. Eloi Maduell Sante Vilanova. They've been doing amazing work, I think, for the past 20-something years. And now, I think, and this is my very personal perception, that they are in their best moment. The first of the best, because the best is yet to come. That was a song by Frank Sinatra, and I think that he was right. So, in the last years, they've been experimenting with a project. En els últims anys han estat experimentant amb un projecte que potser l'heu vist, igual el veureu, es diu ASTRES.
Maybe you've seen it, it's called ASTRES, it's in the Poblenou Park, and the story behind, the inspiration, the research methodology, as well as the, I don't know how to put it, the aim behind the project is to rethink the artistic practice at the times of climate emergency. To do all these beautiful things with LEDs, with lasers, with light. Well, we use a great deal of electricity. So they have opened a question mark about how to keep doing our job using less energy or even zero energy. So let's clap Santi and Eloi from Playmodes.
Jo no tinc fills, però...
I don't have descendants, but I have a computer, so...
Bueno, a veure si va.
Comprovem àudio també.
Anem apinyant, no? Podem entrar el keynote, per fa? Hola, hola. El què?
Ja? HDMI falta.
Ah, l'HDMI. Casa de l'Herrero.
És que no en sabem gaire d'això de connectar. Estem fora de les... Vale. I el so? Vale. Tornem-hi.
Hola, bon dia. S'ha escapat. Què passa? Casa del Herrero, cuchillo de palo. Se suposa que som mig informàtics.
In theory, we are IT experts, but it's not working very well this time. So we are Playmodes, and oftentimes we get the question, what do you do? And it's a difficult question. I don't really know how to answer to it. As you have seen, we work with different formats, from contemporary music concerts, where we play the music and develop the visuals. We also work in light sculptures, mappings, immersive installations. So it's a little bit difficult to answer to the question. Nonetheless, there is an element which has been quite consistent in the last 20 years to all our projects, and it's the idea of visual music, the idea of finding or looking for a deep connection between sound and vision, and pushing the limits of what we see and what we listen. This is nothing new. This is a photogram from an experiment from the beginning of cinema, experimental animation, Walter Ruttmann, Fischinger, McLaren, these amazing artists who started rethinking vanguard art through movement and through this link with music. So we feel somehow heirs, we feel somehow attached to this world from the beginning of the 20th century, the new format back then cinema, and which translated into a great deal of experimentation, combining engineering, art, music, new instruments for optical synthesis, how to draw sound, not only using scripts to create music, but drawing on a thread, on a photogram, and turning it into a sound. So all these ideas that somehow combine in a deep way sound and image, we feel extremely, we resonate a lot with these dynamics. This is our attitude when we face a new project. We like research, and we like these curious images stemming from a different technology, yet with a very similar mindset. I'm always interested in understanding what would happen if I make a link between this and that. Since we met as a musician and a visual artist, we've been fine-tuning this way of playing. This is why we are called Playmodes. And in this descent to hell, sorry, it's pushed us to learn about engineering, right? Because we end up thinking about ways of doing things which are impossible to implement or to execute with the existing technology, with the existing tools, and this imposes an obligation on us, which is developing our own software and hardware devices. Even if today we're going to be rather monographic, we're going to present the item we're going to be introducing in Llum's Barcelona this year. What happened? You're all messy. I know. This week we've been at ISE, at the Llum, and sleeping for 4 hours or even 3 a day is killing our neurons. So again, today we're going to be speaking about ASTRES, which is an example that will reflect all the ideas we have raised before. As he said before, the project started in the COVID-19 pandemic, 2019, 2020. We are in a public crisis context, the climate crisis, the war in the Ukraine. So during COVID, as many artists here in the room, all festivals were cancelled. We were kind of unemployed. So all our planning, all our calendar dropped. And this, of course, gave us time to think, to reflect, and it was a very profitable time. We managed to rethink what would come next, right? So when it comes to energy or to the energy crisis, of course, this had a direct impact in our work dynamics. As you have seen, we use a lot of energy for some of our installations. It's a delicate point whether we should consume energy to produce art or maybe not. This is a quite interesting debate, a difficult one to respond to. But we told ourselves maybe it would be cool to start working on things that are less energy demanding. And this is how we carried out a research, right, on how we could use natural light. Oh, we would need to factor in fire. We focused only on two sources of natural energy, the sun energy and the stars energy. And what else? What came next? Well, of course, we haven't invented this.
Sobretot en el... És com una font de coneixement, no? És a dir, l'estudi dels astres.
The study of the stars is a source of knowledge, of course. The sun is the star that can be seen in a more, let's say, preponderant way from Earth. And in this study of the stars, well, thanks to the study of the stars, we have moved forward. We now understand our position in the universe thanks to astrological observations and light observations, and from here on, humanity could come up with interesting conclusions. Now we know that the Earth is round. At the beginning, it was thought that it was the sun turning around the Earth, and then, of course, the conclusion is the opposite, right? Now we understand that the sun turns around a massive black hole in our galaxy, and all this has been, all these conclusions have been possible thanks to sky observation, and this dates from many years ago. Many civilizations have been interested in this field. So we want to, we're very much used to understanding that. The constellation we see is called the card constellation, but in China maybe they put it differently, or the carriage constellation, sorry. It's not the case from all cultural perspectives, so the sky again is a projection of our knowledge and our traditions. ASTRES, stars, speaks about night, about the night, but we also want to go back to the first experiment with the sun. And the idea behind was to take the light of the sun and placing it in a dark space to be able to work with a free energy source. But of course we needed darkness to contrast with light. And in this first scheme, we had an heliostat. An heliostat is a device that allows you to track the sun and grasp the ray from a specific location. So here is the first prototype of this heliostat. We also like massive things, and this is why it's massive. Its diameter is 1 meter. We wanted it to be powerful. It was an engineering process in partnership with EuroCAT, a research center, which helped us develop this device, which is composed by two engines, one which is a turning engine in the horizontal axis and the other one in the vertical axis. So the idea would be the following. The idea was, how can we test the device? And we came up with the idea of driving the sunlight into a dark space to grow a plant. As we all know, the sun is one of the life sources in the planet, so we want to enable life through a sun which is mediated by us. We developed this weird thing. We're not architects, as you can see. Oh, this thing here. So the tube here in the upper part allows us to bring light into the room in the right hand side of the screen, but only the light which is reflected in the mirror, you can see. So it's a dark room with redirected light, so that only the light which is reflected in the mirror penetrates the room. For that, we had to develop the software to calculate the sun's position, to know the altitude according to the day and the time of the day, etc. And we ended up in a... we were confronted with certain difficulties, which is you need to understand how is your mirror oriented with respect to the orientation of the world. In partnership with UPC, we understood that the best possible way to orient the mirror was to calibrate the mirror through stars. So we did a little hole in the mirror and we introduced a laser, and through a triangulation, we'll tell you what a triangulation is later, we could end up concluding where the mirror is oriented towards, which allows us to track the stars, follow the stars and the sun. Here you can see how the laser ray reflects the mirror and goes all the way into the room and lightens the plants. The picture was taken during the day, and this is the experiment. What would happen if we tried to grow plants for a certain period of time? The plants died. Spoiler. As a result of lack of watering, in fact. So we didn't think about water. What a pity. Typical, isn't it? You make your life so complicated with the millions of microchips, but you forget to water the plants. Well, you know, lesson learned. We've learned a lot, and we have managed to move to the second chapter of the project. The original idea was how can we, I mean, we love contact with nature, we live in the outskirts of Barcelona or not in the city, so we found it extremely poetical. It would be lovely to draw in the sky, to follow the stars, to widen our conception of the universe. We've had to learn quite a lot about astronomy, so it would be interesting to know what an ellipsis is, to understand the rotation of stars, etc. And the first project we did, we traveled all the way up to La Garrocha, a region here in the north of Catalonia, with a laser. And what was quite surprising is to see that the this laser ray, is visible in the air. Humidity, dust, and what was the other element? In this case, the laser is made visible thanks to the humidity in the sky, in the atmosphere. So we've been testing the project for 3 years now, working on grasping a better understanding about how it works, working with more and more powerful lasers. But at the end of the day, the conclusion is that lasers are visible. Yesterday, someone told us, oh, what a pity that it's cloudy today. And in fact, the problem is not so much clouds, but rather luminic pollution. Clouds, in fact, draw funny lights, more graphic lights. Of course, they do not allow you to see the stars and how the laser matches the stars. Nonetheless, it is still very interesting. And yesterday, one of the questions we got was, how is it possible that the ray comes to an abrupt end? We had to ask our colleagues from the academia, but this can be understood by what is called the mixture layer, which goes all the way up to 1,050 meters, where convective movements between heat and dust operate. It's like the skin, the Earth skin, which has a layer of turbulences that combines particles, and this is why the laser stops abruptly. It disappears abruptly. When the density of air changes, the laser is stopped abruptly. But it's an effect. It's not possible to domesticate light. In fact, it keeps moving up, but it's not visible to our eye. The first day we tested the project, as you can see in this picture, it was a very magic moment. The sky was crystal clear, but the line was really visible. It was like projecting into the sky. We can't find a robust explanation about this. I think it had recently rained that afternoon. We think that this effect is a result of a high concentration of humidity in the upper layers, which made the sky a screen, but this is my fantasy, maybe. Yeah, we keep thinking about it. We are interacting, engaging with a natural element, and you know, when you engage with natural elements, every day is a new beginning. There are new starts every day, every morning. So how can we get the star right and get to the star with a laser? It's not that easy. We need to know where we are, what time is it, sorry, and having a star map or catalog, which is a never-ending list of figures that will give you a code for each star, and the two thicker columns inform you about the coordinates. So if you're in Barcelona today, the polar star will be 42 degrees up or 0 degrees north. So this is available in the internet. It's open source, and our catalog has includes the most or the brightest 4,000 stars. I'll speed up here a little bit. It's not that easy. This might seem complicated, but it's not. Two angles. You need to understand the l'azimut. I'm going to kill the interpreters. Azimut is azimut. I don't think there is a translation for that. So it's the angle with regards to the north. Yeah, azimut. We confirm azimuth in English as well. It refers to the angle between the north direction and the point in the sky directly above an object. So 20 degrees, 30 degrees, this will depend on whether you have your own device installed in a flat position on the floor. Of course, you need to be precise. The laser is very thin, so we discussed with our partners at university and the UPC colleagues, the telecommunications colleagues from UPC invited us in, and we discussed with different students in order to grasp how to get it right. And after 6 months, they managed to develop a primigenic way of doing what we call a calibration. Once the system has been calibrated, the laser cannot be moved any farther or anymore, and then anything that happens or that is moved in front, well, then we need to zoom in, and then we'll say, okay, now from here to this star, and now this other star is in this other point, and the laser will have to move, etc. So by doing so, and with the magics that math bring, you can solve the equation, and the calibration system is looped. This would be the process if we had seen a star from Barcelona, which is almost impossible, not only because of the clouds, of course, but also as a result of luminic pollution. The project was designed to be taught or to work in a natural environment with dark skies. But of course, light festivals oftentimes happen in cities, so we've had to adapt in order to be able to work in the city. You know, if you want to pay your bills, go to a place with no stars. Once the system is calibrated, here you can see the 4 points, the area that can be projected, and this is a long-lasting process. You know, you need to leave the laser on for hours and allow it to project the different powerful stars crossing its pathway. There's been a way to prove that the system works and that we can track them. Here we followed the big dipper for 3 hours. And here we have calculated the position of the star and we've updated the position of the laser to follow the stars. And now we are working to move on and to be able to move the project, because when we move the laser, we lose the calibration. And now what we would like is to be able to move the beamer so that we can go from one spot to the next and add an extra layer, which is being able to move the laser beamer. The beamer only projects in a tiny fraction of the sky. Imagine it's like a beamer, a projector. We cannot get any farther, right? If we want to go beyond, we need an engine system that will allow us to move the beamer to project behind or farther. And we need the movement, this back and forth movement, to be concise enough to preserve the calibration. This is not a Pilates machine, believe me, or a Pilates machine. It's the machine we showed you before with an integrated camera to see if we manage to move the projector from different spots. We're not going to be presenting it here. Planes would have made it a little bit more difficult, so it wouldn't have made any sense. to introduce it here in Barcelona. So we're very picky when it comes to coming up with new projects. We always want to ensure that the visual and the sound elements are somehow a unity. Let me tell you a little bit more about the transformation of stars into music. We thought that it would be beautiful to refer to the quadrivium. The quadrivium includes fine arts in Greece. In the old Greece, they already said that the four elements, so geometry, figures in space, music, which is figures in time, and astronomy, which represents figures in time and space. And in this project, even if we are in the 21st century and we are working with super modern, groundbreaking technologies, from an epistemological perspective, we are still going back to the Greeks. We're working with the same matter as the quadrivium.
Llavors, agafant aquesta idea
So, going back to this idea of how we connect arithmetic, geometry, music, and astronomy, what we created was some sort of a system to turn stars into sound, making sound out of data and stars, with different strategies. And maybe it's interesting now to talk about generative techniques. This project cannot be renderized, cannot be rendered. The contents in the sky are always different, and they're always different because the position of stars shifts. It's not the same thing to be in Barcelona on 28th of December or in the southern hemisphere on the 14th of January. The stars that we see are completely different. So we cannot have a video, so to speak, rendered that will fit with the stars. Inherently, the system needs to be real-time. And then there is no soundtrack that you can press play on. It will magically synchronize with the stars. So at a sound and graphic level, we need for everything to be calculated in real time, depending on the stars in the night sky. So what we've done is create a sound system. We use many different strategies for it, but we allocate a note to each star. Sometimes randomly we create a pitch class set, and we allocate different notes to the stars. And the higher up the star in the sky, the higher the pitch, and the closer to the horizon, the lower the pitch. And then we have pitch and pan, and we position these sounds in the multi-channel field with loudspeakers. If you see a star more to the left, you will hear it more to the left, and if you see it to the right, it will sound more to the right. So there's this first systematization of how we turn these dots in the sky into sound. We don't only do it with the dots in the sky, we also draw constellations, also segments, following the same set of rules. We apply a different musical note to each segment. And some stars are brighter than others. If they're brighter, they sound louder, and vice versa. It could be done the other way around, but we decided on that as it seemed the most logical way to proceed. Same thing with segments. If the segment connecting 2 points is less bright, the sound will be quieter, and the other way around. And as we said before, we want a correct spatial position. If the star is on the left, it sounds on the left. If it's more towards the right, it sounds more towards the right. And what we've done in Barcelona is we've created an immersive space. People sit down on lounge chairs, and they have this immersive experience, sound immersive experience. And precisely what we do is to locate the sound of the stars, to localize it through the 13 loudspeakers in the space. We're used to listening to music in stereo, like you're doing now, and it's a very flat noise. It's like looking at a painting. But actually, for a very long time, we've been working with spatial sound, for sound to come from everywhere, because at a perceptive level, it's much more connected to reality. If you're in the middle of the forest and you hear a bird, it's not on a plane. The sound is not on a plane. It can come from anywhere in the space. So we like to replicate this natural phenomenon, to replicate reality based on working with these sound systems. We've already introduced it. We're in Barcelona. You cannot see the stars in the sky. It was cloudy yesterday, so our decision was to precisely have an impact on that. In urban spaces, we cannot see the star. We're missing out on a lot of things. And in a bit of a contradictory fashion, what we do is we recuperate, well, we add more light, but we recuperate this view of the stars, saying you cannot see it, but Vega is here and it's 25 million light years away. It's a white dwarf, and then the North Star is over there, and it is a way of bringing back this vision of the stars and raising awareness on light pollution that we experience in cities and everything that we're missing out on because we cannot enjoy darkness as we should. It's interesting that we're in a light festival and what we're missing is darkness. We have a lot of light, but we're always missing darkness. It's a cultural fact as well. It's a constant struggle that we've experienced almost always when we go to an urban space. And the fact that we adapt to cities, ASTRES developed in a natural space, where we do that, we play around with the stars. Now, coming to a city, we thought it was adequate to talk about light pollution and orbital pollution. At the moment, around the Earth, there is a whole series, a myriad of things orbiting around, hundreds of thousands of objects. All of them are man-built, whole satellites, but there have been collisions, and then these satellites break into million pieces. And the American government especially tracks all of the objects to the size of 1 millimeter to know where they are, because if they want to launch a satellite or a rocket, it can be very dangerous. Actually, in the show, at some point, we talk about orbital pollution. And there is Kessler syndrome, which says that we are at a point in which if there's one more incident, it's a chain reaction. We do not have a butterfly net where we can catch everything. Things have happened with the space station, for example. If someone makes a mistake and we collide, there may be a chain reaction, and the sky will be so full of gadgets and rubbish that there will be no going out of that. They travel at a very high speed, and well, we think it's a very interesting topic. We also must say that during this study we realized that at the moment almost half the satellites in a low orbit belong to Mr. Elon Musk. Out of the 6,000, 3,600, 3,700 belong to him, and every week he launches another 20. So watch out with that, because at some point maybe we will see the stars, but we will see the stars plus the satellites of Mr. Musk. And now onto the performative side of things. Well, if you're very hungry, maybe you can shout at us and we will leave the stage immediately. But if you allow us, and if we find the executable file, the idea now is to tell you about all of these theories and how it is supported by technical infrastructure. There's a very cool thing, which is that Mr. Arola brought us the physical models, and if you work with light, you need to know how light will behave, and you cannot always have the full-size installations in your study. Maybe you have a small study, and you cannot have these big setups. We also work with models, but normally software models, digital models. So we've created a simulator of the night sky where we can see the stars. we will make it a bit more visual. We will make the stars larger so the dots are bigger. This is similar to those apps where you can see the night sky. And this allows us to test things, to make trial runs. The software is a software that we have created. We've been developing it for years. And it allows us to work on a very high percentage of the projects we work on. Most of them run through this software where we add everything that we need. And we will see now, we will start with an example to tell you a bit about the process that we implement stereo mix.
Igual aquí l'àudio hauria d'estar a mig...
Espera.
Ah, vale. Vale, doncs puja.
Yes, we'll control the sound, the volume. So this is for you to see how we get to what you're seeing in the simulator. Everything begins with this module here. This tells us the magnitude is brightness of this star. And we say, okay, out of all of the stars in the night sky in my field of vision, I will filter the ones that are this bright. We have a magnitude of 4 here, and this leads us to 31 stars in our visual field. If we want to see this, we will go to the inspector. And now we have the laser, this red window. This is our field of vision. This is the zenith. And out of all of this, if I alter the filter of magnitude, above 2.1 there are just one star, and if I go to the other side, there are, if I want to see them all, out of the 3,000 that we have, within our field of vision we have about 200. If we reduce it, because we don't want to see so many, we start at this point. I have these stars. What do I do now? Now we have a linear structures sky selector, which tells us, okay, you have a horizontal range with a width, and it can rotate, and it gives us a dynamic selection of the stars. Out of all of the ones we see here, I'll show a few more so it's more clear to see. If we look at the ones selected after the linear filter, this is the one, it's a line that rotates. And this is part of the narrative of the show. We rotate faster, slower, wider, narrower. And then we have a collection of points. I decide which ones I want to work on, and then we will generate two things. First, this is a Dillon graph. It's a triangulation to connect the dots and see what happens. And it's a very aesthetically pleasing way of triangulating the sky. But there are too many lines, I don't want to see them all. So then we go to the graph tree, which builds the tree, or the graph, that contains all of the dots with the shorter length of connecting lines. And this is this drawing. It's one of the strategies. Because we have dots, what do we do with them? This is one of the processes we've carried out, and part of the show will be on linear structures on the sky. And you've seen it, actually, going back to this idea of generating. We are creating generative constellations, random constellations based on the dots we have in the visual field of the laser. These are some in Barcelona, others in Helsinki. They are a specific set today, but 2 months from now they will be different. And now traverse. You've seen that this can be used like an instrument. If we select more or less dots, the sound reacts to what is happening. When a segment changes, I've disconnected the angle from the automation, and I can adjust it, and stars will appear and disappear in each position, and we can see them and hear them, and the drawing changes. And if I make it narrower or wider, it becomes wider and wider and wider, or narrower. And it's a way of, it's like the tracing, the expression of what we are doing. It's a bit nerdish, but the idea is how you adjust them to have some visual expression or sound expression. And another example of this idea of sounding, we draw a graph, and every time we find a star, a new sound is heard, and every time we remove one, then we hear a different sound. And there are more things inside. And yesterday, some people came and said, "What does interiuses mean?" In our quirks, we said at the beginning, we have such strange ideas that we cannot use commercial software, so we create our own sound generators. We create a specific synthesizer to work with stars, and this synthesizer, they are here. It's beautiful. They receive data from the discovery of a star or the blurring of a star, and they turn all of this into music. Maybe the best thing is to just stay silent for a bit and listen to it.
Llavors, ahir en Marcelo preguntava...
Yesterday, Marcello asked, and he may be around, he says, what takes precedence, music or graphs? But what is music? Music is the organization of sounds over time. Here we're working with sounding. We sound what happens at a graphic level. So actually, when we're creating graphs, we're creating music. The organization around time comes from how light behaves in a dynamic manner over time. So the graphs are the ones playing music. And then there's sound design, whether this is a bell or a flute or whatever, or what scale is used. But the organization of sounds in time actually is defined by the behavior of light, which is something that we like, because this is what we go for. We want to see this unification of both languages. And we used to, or before we were talking about this idea of spatialization of sound. Yes, under a stereo mix, but it's not, I cannot hear it. No, it should go through U2 and then it should be audible. So you can see this dot. Imagine these are the 13 loudspeakers, and this is a source of sound that we want to distribute throughout the space. So we calculate. Why is it sounding now? Because here we have two loudspeakers. This is number 1, this is number 2. We only hear the sound when the dot comes near 1 and 2. If we had 13 loudspeakers, we would hear it all the time, which is what happens at the installation. So we measure the distance of the sound source to the loudspeakers, and the volume is linked to how close or far is the object to the loudspeakers. And maybe to finish with this section on sound, there's a narrative part of the show which is quite relevant, where there is a voice that tells us what star we're seeing, how far is it, what spectral type it is. And this we've done in collaboration with Pompeu Fabra University, a group which is called Colectivat, and the Supercomputing Center of Barcelona. They allowed us to use their text-to-speech models. We need this voice to be able to tell us what star we're seeing at the moment, and we cannot pre-record this because we do not know what star we'll be seeing, and it depends on whether we're in Barcelona or Helsinki. It will be different again. So what we've done is we've integrated in our software this talking machine, which helps us narrate the stars. Here, for example, if I choose this star here, come on.
A la constel·lació de Cygnus. És un gegant taronja.
It is an orange giant with a visual magnitude of 2.4 at a distance of 57.2 light years from the Earth. Its approximate mass is 6 times that of the Sun. It is telling us about this star that was just selected, what's its name, where it is, and this is something that we use throughout the show. This is a yellow star like the Sun with a visual magnitude of 3.2 at a distance of 120.8 light years from the Earth. Its approximate mass is 8 times that of the Sun. This is the narrative side of things. From the beginning of the project, sometimes we've done it with people talking about mythology, the mythology of constellations. Then we did it with Elvira Cano on darkness, the culture of darkness, the need for darkness. And this time we did it with an AI that talks in Catalan, which is something we were interested in, and we could not have a person knowing all of the stars doing it. And also, we wanted to disseminate knowledge on stars in the city, claiming the lack of, or the presence of light pollution and a bit of a pedagogical effort. We have not performed much, but I think, well, it was more like a performance of the mind. Thank you very much.